Hey Precalculus, here we go with section 7.3, day 2. Trigonometric equations, and this is the last day of notes before we're going to stop and take a half test for the first half of section 7.3. Okay, I'm going to do, we're going to get more complicated with how we're going to solve equations. So look what we're doing here. We're factoring as a review with quadratics because we're about to have to factor trigonometric equations. Take a look at that. Okay, factor this nice easy polynomial. Here's some review for you. Some of you guys really enjoy taking this a, b, and c and multiplying a times c and taking factors of that product and see if they can add up to b. You're doing the same thing I'm doing, but I'm doing it in a problem-solving scenario, not a series of things that you have to remember how to do in order or you can't do it right. Okay, if I'm going to have an x squared here, it had to come from these two things multiplying to get me x squared, and those have to be x times x. And if I'm going to have a 6 here, it's got to be two things that multiply to give me a 6. Now that can be a 2 and a 3, or it can be a 6 and a 1. And instead of writing down all the pairs of factors like you guys do, what I'm going to do is I'm going to, in my head, go, can I get a 2 and a 3 to add together to turn into a 7, or can I get a 1 and a 6 to add together to get to be a 7, and it's got to be the 1 and the 6. When this third sign is plus, it means these two had to be the same sign. And to get it to be a -7, they've got to be a minus. So look, if I multiply it out, I get x squared, I get minus 6x, and I get minus 1x, gives me my -7, and -1 times -6 is +6. That's how I factor by what's called the guess and check method. Now, slightly less easy is when you have a 2 here. Okay, so I'm going to put a 2x in the first set of parentheses and an x in the second set of parentheses so that the two things will multiply to give me 2x squared. That does make things a little more complicated because it's not just a 6x and a 1x. Whatever I put in that spot will get multiplied by 2. Okay, I'm trying to get two things that will be opposite signs. I have factors, these two things have to multiply to give me a 5. It's a 1 and a 5, or it's a 5 and a 1. Now, I want them to end up being a 9, so I'm not going to put the 5 here and the 1 here because it would be a 2x and a 5x. Now, that actually gives me 7. But if I put the 1 here and the 5 here, I get a 10x and a 1x. I can make 9 happen out of there. So I'm going to put the 5 and the 1 because I know that's the way it's got to go. The 2x and the x give me 2x squared. The 1 and the 5 will give me a 5. They have to be opposite signs. Now I want to get a +9 out of this, so I'm going to put a plus there. Why? Because 2x times +5 is +10x. And I'm going to put the minus there to get the -x, so that 2x times 5 being 10x and -1x will get me the 9 I'm looking for. The first two multiply to give me 2x squared. The last two multiply to give me -5. And I do get 9x in the middle. Okay, and a horror show. Well, look, now, not only do I have to multiply two things to get me 9x, but I've got all kinds of things that could be the 24. But look, I'm going to write up two sets of parentheses because this could be 9x and 1x, or it could be 3x and 3x. That does make this tougher. You might have a better time with multiplying a, b, and c, or a and c, but 9 times 24 is a real big number. So I'm going to stick with the guess and check method. 24, I'm trying to get this to be a 6. Well, it's not going to be a 1 and a 24. Because if I put a 24 there and a 1 there, I've got 9 and 24. That doesn't make 6 happen. 2 and 12. I could put the 12 here and the 2 here. I'm going to get an 18 and a 12. 18 and 12 would give me 6 if I'm subtracting them. Let's see. Put a... let's see, a 2 there and a 12 there. I would get 18x, and I would get 12x. And if I subtract them, I will get what I'm looking for. So let's see, if I put the 18 as positive, and I put the minus here, I have 9x squared, I have plus 18x, I have minus 12x, that's going to be plus 6x, and then I have minus 24. Look at that, I factored it. You can also factor this one with the 3x's, I think. So if I go with a 4 and a 6, I'm going to go with a 4 and a 6, I'll get an 18x and a 12x. Look, I got the same thing, an 18x and a 12x. So let's see, I want the 18 to be positive, so I'll put a plus here and a minus there, so that I would get 9x squared, I would get plus 18x, and I would get minus 12x. How is it possible that we could get two separate things that give us the same answer? We actually did get the same thing. Watch. Can't you factor something out of here? You can take a 3 out of both of these, right? If you take a 3 out of both of these, look what you get 3 times. It's 3x minus 4, and it's x plus 2. 3 times 3x minus 4 times x plus 2. I can't take anything out of this, but I can take a 3 out of there. If I do, I'm going to take the 3, I'm going to write it out of there. I get 3x minus 4, and I get, since I took 3 out of there, it'll be x plus 2. Look at that. I ended up with the same thing. So either way I went, I actually do end up with the same thing. Okay, we're not going to have to factor anything that's hard. That's that hard. We're going to have to do these kind of things with the trigonometric expressions, okay? So here we go, solving trigonometric equations. From 0 to 2 pi, I'm going to have to factor this thing. Think of it as 2x squared minus 3x plus 1 equals 0. Just think of it like an x. You could, if you want, you can do this every time. I don't think you should do this, but you can. You could rewrite it with an x, and then you could just factor it like this. And then once you're done, put sign back in after you're done factoring. It's actually called an x. That would be called an x substitution. We use u substitutions in calculus. What I think you should do, I'm going to go over here. I'm going to write 2 sine squared theta minus 3 sine of theta plus 1 equals 0. I'm going to write 2 sets of parentheses. I got to make them bigger because I got to write words in there now. Look, to get 2 sine squared, I'm going to need 2 sine of theta times the sine of theta. If you multiply those together, you get 2 sine of theta squared. That's how we write it, 2 sine squared theta. To get this part to be a 1, I just put a 1. Okay, and then see it the same way that you saw these. So look, I'm going to have a 2 sine of theta and a 1 sine of theta. They have to be the same sign, and I got to get negative 3. Aren't these both just negative 1? 2 sine squared, there it is, minus 2 sine of theta minus 1 sine of theta is minus 3, and then plus 1. If you want to do this over here, you can do it. Write a 2x and an x, put a 1 and a 1, and you'll figure out they have to be the same sign, and I got to be negative 3, so it looks like that. And then you would just rewrite it with sign in it instead of x. I think you're better off if you get used to doing this. If you still want to write it this way and then multiply 2 times 1 and get 2 and come up with the factors that add up to be a negative 3, then have to write it at the end this way, you go ahead. It's just going to take you longer to finish your tests. Okay, now why do we factor? Why do we ever factor? If this was set equal to 0, I would then set this equal to 0, and instead of having 3 things plus or minus, I have 2 things times each other. And so I can set this one equal to 0, and I can set this one equal to 0 separately because they're times each other. Whenever you have 2 things times each other that equal 0, one of them's got to be 0. So you take both of these things in parentheses, set them equal, and you get x equals 1, and you get x equals 6. That's why you factor. So you can set equal to 0 and set littler expressions equal to each other. So look what we did here. We took 3 things plus each other equal to 0, and we factored it so it's 2 things times each other equals 0. So now we're separately going to solve 2 sine of theta minus 1 equals 0 and sine of theta minus 1 equals 0. So I'm going to add 1, and I get sine of theta equals 1 divided, and then I'm going to divide by 2. And here I'm going to get sine of theta equals 1. I skipped a step there. Hopefully you guys are okay with that. I added 1, and then I divided by 2. So look, I'm looking for every angle from 0 to 2 pi. So let me draw a unit circle where sine is 1/2, sine's 1/2 there, and sine is also 1/2 there. And also where sine is equal to 1. It's also 1 up there. So here are my answers. X equals, I had a x or a theta, theta equals pi over 6, theta equals pi over 2, and theta equals 5 pi over 6. All right, there's one. I had to factor first, then solve both of them being set equal to 0. Okay, that's a big jump from what we did yesterday. You'll get a couple opportunities to try them for homework. Let's just kind of see how it goes. All right, now I'm going to solve 0 to 2 pi. Look, I got tangent squared plus tangent. Now it doesn't look like there's much we can do here. And please stop telling me that we should subtract tangent to the other side. You just make me angry when you do that. Look, there's a tangent in both of these things, I can use the distributive property to factor tangent out. So look, I'm going to write the original over here. Tangent squared theta plus tangent of theta is equal to 0. And then I'm going to use the distributive property, and I'm going to, and that is factoring, by the way, use the distributive property to move something out. That's just a different kind of factoring. If I take tangent out of this one, I'm left with tangent. If I take tangent out of this one by dividing, I'm left with 1, all right? So that would be tangent squared, and that would be tangent. Why do we factor? We factor so we could set these equal to 0 separately. Tangent of theta equals 0 for that one. And for this one, tangent of theta plus 1 equals 0. That's already isolated. I am going to subtract 1 here. Okay. Draw my circle where from 0 to 2 pi is tangent equal to 0. Well, you guys, tangent is the sine of theta over the cosine of 0. For that fraction to be 0, sine has to be 0. Where is the y value 0? That's here and here. At the point 1, 0, and negative 1, 0. That's where the sine is 0, so this fraction is 0. So tangent is 0. Now where is tangent negative 1? We talked about that in class yesterday. For tangent to be 1 or negative 1, it's got to be a 45-degree angle because y over x can't turn into a 1 unless they're the exact same thing. So that's going to be at this 45-degree angle and at this 45-degree angle, because up here it's negative positive and down here it's positive negative. And when I put that y over that x, I get negative. Up here I don't. Plus over plus or minus over minus is not negative. So my answers, theta equals this one, 3 pi over 4. This one, pi. This one, 7 pi over 4. And this one is 2 pi. Or I guess I could have said 0 if I had to, right? Okay, a lot tougher than yesterday, and I'm going a little fast, so if you have to, rewind it, listen to it again, maybe before you try your homework. Now we're going to do something completely different. Oh boy, here we go. A list of trigonometric identities. That just sounds intimidating just when I first say it. I'm going to give you a definition of what identities mean in the second half of this chapter, and we're going to do something called verifying trigonometric identities, which is going to give you nightmares. Something to look forward to. Okay, the reciprocal identities, these are a result of SOHCAHTOA and the definition of secant, cosecant, and cotangent. Okay, cosecant is just 1 over the sine of theta. You already knew that. I'm just writing these as a complete list of the identities we know so far. These will be new for you today. Secant is 1 over the cosine of theta, and cotangent is 1 over the tangent of theta. Okay, get those written down. Then we'll do the other ones. They're just the flippies of these first ones. Sine is 1 over cosecant of theta. Cosine is 1 over the secant of theta. And tangent is 1 over the cotangent of theta. Those are your 6 reciprocal identities. The quotient identities. Sine over cosine is another way to rewrite tangent. And cotangent is cosine over sine. We have used those a couple of times just to figure out things like the cotangent of pi over 3. We just went right to x over y, right? We used the quotient identities. This is new, all right? It's going to make sense to you, but we're going to use it on the next page to solve another equation, okay? These come from using SOHCAHTOA and the unit circle, and are you ready for this? The Pythagorean Theorem. It'll be the second time we use this. The first time was to show that the radius is always 1, and why x and y ended up being sine and cosine. I think I said those backwards, but you guys get it. Here's what I want you to do. Draw, maybe use the 45-degree angle right in the middle. Turn this into a right angle right here, okay? Turn that into a right angle, and that's a point xy, which we also know is a point cosine of theta and sine of theta. In this case, I use theta as the 45-degree angle, but I'll write theta in there, right? Now, watch. I could write this as x, or I could write it as the cosine of theta, because the x value is actually the cosine of theta. And here on the side, I'm going to write this as sine of theta, because the y is actually sine of theta. Well, ready? Don't you know that a squared plus b squared is equal to, c squared in any right triangle? where c squared is the hypotenuse. We know that's 1, right? Put a 1 up there. So I'm going to go right, and I'm going to write the first of the 3 Pythagorean identities. Ready for this? A squared plus b squared equals c squared. Sine squared plus cosine squared. Y squared plus x squared equals 1 squared. Right? Doesn't this go? Sine squared theta, that's one side squared, plus cosine squared theta, that's the other side squared, is equal to 1 squared. Right? So look, sine squared theta plus cosine squared theta equals 1. 1 squared is 1, so I can just write it as 1. That is your first brand new trig identity. That is true no matter what angle I'm talking about. Put 20 degrees in there. You want to put it in your calculator? Put it in your calculator. 20 degrees, watch. I'll put it in my calculator because you never believe me. Ooh, look at histogram. Okay, I'm going to clear this out. I'm going to go to mode, and I'm going to do degrees just because you're more comfortable with degrees. And watch, I'm going to go parentheses, sine of 20 degrees. Oh, see, I got parentheses. I'm going to square it. Ready? And I'm going to go cosine plus the cosine in parentheses of 20 degrees. Finish that parentheses. I'm going to square that. I'm going to add the sine of 20 squared plus the cosine 20 squared. Ready? It's equal to 1. Look at that. Doesn't matter what angle it is. Sine squared theta plus cosine squared theta is actually equal to 1. Now for this one. Okay, I'm going to write some stuff here at the bottom. I'm going to write sine squared theta plus cosine squared theta is equal to 1. Then I'm going to divide all 3 of these, which is an okay thing to do algebraically. I'm going to divide all 3 of them by sine squared theta. Okay? This doesn't work without the squared, by the way. It's not a plus b equals c. It's a squared plus b squared equals c squared. So those have to be squared. Okay, sine squared divided by sine squared is just 1, isn't it? That would cancel. Cosine squared over sine squared, look at that right there. Cosine over sine. If I square both of those, I just square this. That's actually equal to cotangent squared theta. And then 1 over sine squared, look at that. If that's squared, that's squared and that's squared, I just square that. So it's equal to cosecant squared theta. Guys, I got a second version of the Pythagorean identity for you. And it goes 1 plus cotangent squared theta is equal to cosecant squared theta. Now, we're not going to use that today, but I just want you to see all of them. And I got one more thing to do. Watch, I'm going to write the original again. Sine squared theta plus cosine squared theta equals 1. And what I'm going to do this time is instead of dividing by sine squared, I'll divide by cosine squared. And watch. Divide by cosine squared theta, divide by cosine squared theta, divide by cosine squared theta. That's an algebra trick you've done forever. Divide everything by like 2 if you're dividing by 2. Sine squared over cosine squared. Take a look at it. Sine over cosine is tangent. Sine squared over cosine squared would be tangent squared theta. Cosine squared divided by cosine squared is 1. And 1 over cosine squared, let's look up here. 1 over cosine is secant, so 1 squared over cosine squared is going to be secant squared theta. So it's the case that tangent squared theta plus 1 is equal to secant squared theta. Now, what do these things mean, these identities? It means anywhere I see cosine over sine, I could rewrite it as cotangent. Anywhere I see sine squared plus cosine squared, I could rewrite it as 1. Okay? Or, I'm going to go one further, right under here. If I want to get sine squared theta by itself in this identity, I would subtract cosine squared, wouldn't I? So I would get that 1 where it is, minus cosine squared theta. So there's another version of the Pythagorean identity if I subtract cosine squared. Now anywhere I see sine squared theta, I could replace it with that if I want to. Okay, let's go to the next video.